Okay, the theme for this week is exploring data, and this is absolutely key, and you really want to spend more time on it in your discipline and in your career than we will in this class. Proportionately, we talk a lot about modeling, but you really want to spend a lot of time with your data. And the reason is because without good data, and without you knowing how good your data is, where it's good, where it isn't, what the issues with it are, you can't build robust, reliable models. Or you might think you have a robust model and someone goes, oh, but your data had this problem. And if you didn't know about it, that can be embarrassing. And think of all the different individuals and software packages and pieces of equipment that you've used to go from field data all the way through to publishing your results. That could involve field technicians, software programmers, statisticians who wrote the stuff we'll be using in R. A lot of them aren't software programmers, and then you have software programmers doing statistics sometimes, which is really what I am. Instructors like me, are you always going to trust me? GIS technicians could make mistakes, wrong projections, undefined projections, all kinds of issues. Other researchers that you're reliant upon to cite their research and their methods, which sometimes are then disproved later, or yourself. And Zen and the Art of Motorcycle Maintenance is an old classic book that I really like because it talks about how there are people who work on their own motorcycles and people who are like, oh no, you want to have a trained professional working on your motorcycle. Well, I hate to tell you, you are the trained professionals from now on when it comes to modeling. You want to be the person working with your data. You want to know it all the way from the field, all the way through to release, as well as you can. We'll talk about why. So we're going to be doing mostly regression or correlation modeling. The word regression is kind of awkward. It doesn't have a lot of meaning. It's an anachronism in my opinion. We're really correlating things. We're correlating our independent variables with our dependent variables so that we can do predictions with a model. What all of these methods do is create a model in some n-dimensional hyperspace. So multiple independent variables predicting what's going to happen, usually with a single response variable. There's math used to do this that defines the type of model that we're going to use. We're going to look at a number of different approaches, different types of mathematics. Statistics are used to optimize the parameters, and then we'll talk about different options for model evaluation and predictor variables. And we'll be doing that over the bulk more than the first half of the class. We've already talked about linear regression. You'll see this again because, again, the mathematics is relatively easy and we can visualize it pretty easy and look at it even in pseudo 3 dimensions. So we can look at multiple linear regression. There's an example like we looked at last week with 2 predictors. We'll also look at nonlinear regression because a lot of the data that we have and a lot of the phenomenon we're trying to model are nonlinear in natural resources. It's really hard to find a linear model. Some of these methods include continuous regression, which is the ones we'll start with and the most straightforward. Linear regression, generalized linear models, and generalized additive models. Each of these has its place, but also each of them are defined by the phenomenon that we're trying to model and the data that we have available. Linear regression we use when we have data that we would expect a linear fit to, which is not as often as you might think unless we do something to linearize our data. Generalized linear models, or GLMs, we use with presence-absence data a lot. Logistics is one of the distributions that we'll use with generalized linear models. Generalized additive models are much more flexible. They're very cool. You can use them with all kinds of things. Categorical regression trees are a very different approach. We'll talk more about those tree approaches. And then we'll talk about some machine learning methods, including maximum entropy. One example, just a simple example, one that I worked on was brown shrimp size, and notice that we had tons of data. And there's this interesting correlation that as shrimp get longer, the depth goes down. In other words, shrimp are born in shallow waters, and then they migrate out into deeper waters. And one of the discussions we had over and over again, well, which is the independent, which is the dependent, right? Is it the length of the shrimp that's dependent upon depth, or is the depth dependent upon the length of the shrimp? And I put this up because I think we did it backwards, right? I think the depth is the independent one, brown shrimp, depth is depth. You can go pick your depth, and then you look at the depth and you find out what the size of the shrimp are. This is a pretty strong relationship given tons of data over many decades. All right, so I mentioned Plant's book. It's an amazing book. I don't require it, and it's great to have it on your shelf to look at it, go through it, as with some of the other books that I mentioned. But he uses measured value and response variable and explanatory variable. Those are fine, but I do prefer response variable. I will use measured values specifically to talk about field data, out where you're making measurements, because there it makes sense to me. I'll also use covariates, because I can't help it, because that's what I learned when I was doing modeling, learning modeling. I'll also use predictors when we're using independent variable to predict, but I'll try to use response and independent as much as possible, because those are really the basic and I think the most general terms for that. So a real quick example of the type of stuff we're going to be doing. Here we have precipitation, and based on precipitation we have different habitat quality for Doug fir. In other words, Doug fir likes it wet. If you go down to Southern California, the Mojave Desert, Arizona, New Mexico, you don't see a whole lot of Doug fir. Certainly not in the drier parts, the deserts. No Doug fir in the desert. Okay, what you do find is when it gets wetter, like around here, you find lots of Doug fir. So there's this relationship that the habitat quality specifically for Doug fir gets better as precipitation increases. And this, of course, would be a logistic distribution, logistic relationship. Bimodal distribution, sorry, I should use that correctly. So bimodal in that there's either zeros or ones, and then the mathematics is called a logistic. We'll talk more about that, I think, next week. So the way we go about doing this is that we have our predictors and data, we have a model, and then from that we get a prediction. To make this clearer, we take field data, okay, points. These are actual Doug fir points from the FIA, Forest Inventory Analysis data set. Very cool data set. And we match that to covariate, in this case precipitation. From that we do model selection and parameter estimation, important terms. Model selection being picking the model, so in this case a logistic model, and then parameter estimation, estimating the parameters that go into the math to define the logistic. That gives us our model, or mathematical relationship. From that we can then take a predictor, which in this case is the same as the covariate, same raster data. We feed it into the model, and that now gives us a prediction. The difference between the prediction and the field data is that the prediction has a value for every pixel in the original raster, where the field data doesn't necessarily have that. Here we're just showing the presence points, but I also use absence points for the areas in California that didn't have Doug fir. So it's a presence-absence model, or binomial. Okay, so the other thing we need to do is now, once we have our prediction, is we need to validate it back to our field or sample data. And we'll talk quite a bit about that. When we look at that with what we're really doing, and specifically in R, is that we tend to have our field data, which tends to come in an Excel spreadsheet. Lat long is very common, and then some type of indication of presence and absence, which in this case is actually a F3, which I believe is height. And then we have our predictors, precipitation in this case that we pump in here, precipitation here, mean temperature here. From that we create our model, or we run software that creates our model. That gives us our model parameters, which really represents our model. And then from that we can take our precipitation data, or really all of our covariates, convert those to a point data set, convert that into a spreadsheet. Now we have mean and precipitation, but we have it for every cell in California. And then we can run our prediction and predict what's the habitat quality or the chance of occurrence or any number of other things in our final output. We get a raster for that. So this is really the process, and this is what you'll be doing in R. This is exactly the process, because we put data tables or data frames into R, which look a lot like Excel shapefiles, simple ones, simple tables. And then we'll do another table for our prediction, and we'll get out these rasters, and we'll use ArcGIS or Blue Spray to do the extraction and the visualizations for these. Okay, so to do this, I give you a little bit of an overview so you can get a taste of where we're headed. But to do this, we've got to have data, right? That's really key. The response variable comes from the field data. The covariates can come from the field, or more commonly, they're remotely sensed so that we get a continuous raster. Predictors are also typically remotely sensed almost all the time. They sample as covariates for training. I'll talk about that in a second. It can be different for predicting for new scenarios. In other words, if your covariates come from the field, that would be where you went out in the field and you made measurements when you collected your field data. Now there's an issue with that because the covariates with your field data normally don't cover everything, right? They're not covering your entire area of interest that you're modeling in. So you can build models from those, but we have to be a little careful about it. I'll talk more about that later. Your predictors, again, usually are continuous, but to build our model or train our model, we can sample those predictors. In other words, we can pull out values for covariates where we have field data in our predictor layers. Hope that's clear. Let me know if it's not. And then if we have a really good, robust model, we could do prediction. We could take a different layer. In other words, we could take precipitation for California 20 years from now and see, well, what's going to happen to Doug fir habitat in 20 years with climate change. That's really where we're headed. This is really important because this is what we can do to predict for different future scenarios with the world changing the way it is. Okay, now some of the things that we want to ask as we get our data, as we start playing with our data, we want to ask is, what's the spatial uncertainty? How is this data collected? Was it interpolated, which means it's not going to have very good spatial certainty? Or was it with a high resolution GPS, maybe sub-meter? That'd be amazing. What's its temporal uncertainty? One that we tend to forget about, but is really important, because what if our data is old and doesn't really match the real world anymore? Our measurement uncertainty. How good was our measurements? Every measurement has uncertainty in it, but it's rarely quantified. And what we're really looking for in each of these is not, is it perfect, because no data is perfect, not going to happen, but will it answer your question? In other words, can you get data that's good enough to answer your question? And if you're looking globally to build a global model, you're not going to need 1 meter data. You don't. 1 kilometer is going to be great. In fact, you're going to have a hard time dealing with the size of the data if you're trying to do it at 1 kilometer. Often they do it at 1 degree for climate models, which is 110 kilometers squared, huge pixels, right? If that's fine, great, do it. But if you're modeling something in Arcata Forest, you might need 1 meter data or at least 10 meter data. So it's going to depend upon your question as to what the accuracy and precision of your data is that's required. Okay, so again, what's the and that was for response variables. For covariates and predictors, you want to ask those same questions, but you also want to ask, does the collection time of the covariates match the field data? In other words, was your predictor layer, especially like with precipitation, was that collected the same time as the Doug fir locations? FIA data was collected over several decades. Planet's changing, precipitation is changing. New precipitation data for this year isn't going to match precipitation for 30 years ago. Do they covary with the phenomenon? And this is where we hit the literature, do searches, find out, has Doug fir been shown in past studies to be dependent upon precipitation? Yes, it has. We cite that, off we go. And another question we ask is, do the covariates correlate? Biggest one I get into with this is elevation versus precipitation and temperature. Elevation is often put into models. I don't like it. I don't want it in there because it co-varies with precipitation and temperature. And I argue sometimes with folks, but plants don't care about elevation. They care about temperature and precipitation. As you go up in elevation, temperature and precipitation change. But we have layers for temperature and precipitation from bioclim, and especially now from PRISM, that are highly accurate, cover the entire country. So I'd use those instead. Okay, so hopefully you've heard of accuracy and precision. These are two types of uncertainty, accuracy being bias, or that shift in the mean that we mentioned a little bit with standard deviation. Precision is repeatability. Can we get the same results over and over again? These are two different terms. Please memorize them and look them up if you need to. Reliability is do we have a consistent set of measurements? Okay, so are your measurements reliable, and are they consistently reliable? So in other words, Field teams tend to not do as well right before lunch and right before they stop working. So their reliability goes down. That's a bit of a problem, and that's been shown. Resolution, or the fineness of detail, not necessarily the pixel size in your images, because that can fool you, but how good is your data at resolving what's going on the ground? Is it capturing what's really happening on the ground? We'll talk more about that. Logical consistency, does it make sense? Structural rules, attributes, relationships. Regularly I get data that has the wrong thing in a column. I don't know why, labeled latitude and somebody's initials are in it. That happens all the time. It's weird. Longitude, not as much, but people like putting initials in latitudes. So just gross, broken problems. And then is it complete? Okay, types of errors. So gross errors. These come often from transcription when people are transcribing data. Bad thing. We need to get the data into electronic form and keep it there as much as possible, because humans will make those kind of errors. Not the computers don't have errors in them. That happens too. Sinks and dems are ones we don't deal with as much, but now we have dimples in dems, which is a different and even more annoying problem. Random errors are going to be like our residuals, and these we can estimate using probability theory, and we'll talk a lot about random errors. And then there's systematic errors, which you don't see as often, but drift in instruments. Instruments will warm up over time, especially if they're in the sun, and then that will change their measures. And then they'll cool off in the evening and you get different measures again. Very frustrating. The drop lines in the Landsat that we had for a while, that would be another systematic one. Okay, gross errors, I mentioned some lat long, just the wrong things being in there or being reversed. Lots of zeros in longitude, so that they're latitude, so they just end up on the equator. Dates, I'll talk about extending dates in databases, that's a problem. And then measurements, always dealing with inconsistent units. We're still dealing with English versus metric. People put an English in one, metric in another, and not labeling it. So when you put them together, it doesn't make any sense. Inconsistent protocols, different ways of collecting data, still a big issue. And in that, you've got to remember, what can you expect from a field team? You get out in the field, hopefully all of you have done field work or will be doing it. You think about it, you're working all day, you're working hard, especially if it's hot, you're tired. The quality of your work is going to go down. So you want to make your protocols as simple and straightforward as possible, and train your field crews on them. All right, so here's some examples. One of my favorites is the occurrence of polar bears. Polar bears have now been seen in not only Arizona here, but Denver, here in London, and they're moving across Europe. Well, that's because the Global Biodiversity Information Facility, or GBIF, has everybody putting whatever data they have in it. We've even got one here in the Indian Ocean, though we don't know why that one's there. So these are in zoos, by the way. That's where these are coming from. There are no polar bears in London or Arizona that aren't in zoos. So that's a problem, because the zoo folks are going, well, there's a polar bear there. But if we use that to build a habitat model, it's going to really throw things off. So those would be examples of gross errors. This is the systematic Landsat scan line error, which you may see if you work with Landsat data from about a decade ago. They're really annoying. You can stitch them, but that then stitch them to get rid of these gaps, but that then introduces another type of uncertainty where it's stitched. All right, so to qualify data, number one thing, put it in a map, look at it, zoom in, zoom out, zoom around, check that data, symbolize the attributes you're going to be working with, make sure it feels like that data is really solid and is doing what you think it should. Examine the data values. I've gotten data sets that had nothing after the digits, after the decimal in lat long, which means it was 110 kilometer data. Not good. We'll talk about patterns. Documentation, is there documentation there? If there's no documentation, that reduces the chance that your data is good quality. And then you want to look at the measurements themselves. And we'll talk about some different methods for that. Occurrences are hard to evaluate because we don't really have tools for that other than putting them on a map. But if they're binary, categorical, or continuous, you can histogram them and see if they look good, right? Are they doing something strange in the histogram, or are they doing what you expect? This is an example some of you may have seen before from me, where a graduate student up at Oregon State was going to build a model with fire, and he had not mapped the data and zoomed in and out. And if you just look at it at this scale, it looks fine. But when you zoom in, suddenly you find out it's at a 4-kilometer grid. Someone probably converted it to raster, converted it back again, and that meant everything was now, well, not everything, part of the data sets, even worse, part of the data sets are a 4-kilometer grid, which means he can't run it at a 1-kilometer model, which is what he planned on. So that's a problem. Map it, take a look at it. Significant digits. How many digits do you need to represent 1 meter? I think this is on a quiz. Lat long is 5, UTM, none, right? It is 1 meter data if it's in UTM. There you go. Okay, covariate qualification. So same with covariates, map them, check the documentation, examine the data, look at how many digits. We've gotten burned on temperature and precipitation layers where they truncated the digits. Okay, that's a problem. Look for repeating patterns, artifacts that are in there, and again, histograms can be good. Here's an example. That looks like a pretty good histogram for CONUS, Continental United States Annual Precipitation. But what's up with that one? And I apologize about the background. There we go. What's up? What happened? Take a look. Think about it for a sec. This data has been messed with. Somebody went in there because coldest month, right? Minimum temperature coldest month should not bounce up and down like this, right? There's no reason for that to happen unless you somehow in processing introduced an artifact, specifically high frequency of some type. Okay, it should look like that. That's more what we would expect. So there's different tools here to get different artifacts. Histogramming being a very good, easy one to use. Here's some other examples. Okay. Now in this one, what you want to do is if you looked here, you might think, oh, everything's okay. Yes, these are graphs in R. Please do not put in things with $signs in your stuff. Okay, but if we run it with the default bin size, we're not necessarily going to see everything we want to. Crank up the bin size or make them narrower, smaller, larger number of bins. Suddenly you're starting to see much more of what's going on. And here's just some other examples of doing that. And here you can start to see there's something a little strange going on. Now that doesn't mean we don't use the data, okay, because there's these gaps there. That just means we want to use it, you know, with a grain of salt, know that these gaps are there, and not assume that our models are better than they are. Okay, one of the things we need to check is if our covariates correlate. Okay, again, these are our independent variables, or our covariates. Typically that's done with correlation plots. You can also measure it with Pearson's product moment correlation coefficient, or Spearman's rho, which is the non-parametric correlation coefficient. So Pearson for linear, basically we'll talk about parametric, non-parametric, and Spearman's for everything else. Okay, Spearman's is very flexible. Correlation plots. Here's a correlation plot. Okay, so the basic idea here is we've got a bunch of predictor variables, which you can see coming down here. Okay, so we've got whatever that says, distance to roadway, aspect, slope, topography roughness index, topographic roughness index, TRPI, another one of those. Anyway, bunch of different covariates that we might build a model with. And then these graphs show the correlation between those. In other words, these are scattergrams, plotting those, and then these are the correlation coefficients, okay? So immediately we go here and we go, aha, there is a very strong correlation between NDVI and greenness, which makes sense since greenness predicts vegetation vigor. Now, same thing with greenness and whatever that one is that I can't read very well. Okay, don't put this level of detail into your reports. Pull out just those covariates that are important to you. Now, at the same time, we can also look over here and go, aha, this has a 0.94, which is a very strong correlation. NDVI to greenness, 0.98. And what that means is that we would not want to use both NDVI and greenness in a model. That can make our model look better than it really is because we're using covariates that already correlate. In other words, they're duplicating the modeling effort. So you would only want to use one of these that has a correlation coefficient of definitely 0.9 and above. 0.8 probably as well, even 0.7, 0.6, kind of like, but you look at the rest of these and it's like they're very low. Okay, so it depends a little bit, and this is why adjusted R squared is important, because with regular R squared, if you have multiple covariates that correlate, using those to predict your response variable, your R squareds will look better than it should, and adjusted R squared takes out some of that to have them look better. Here's some other ones for looking at California. This is kind of fun. This is X and Y, okay, which makes a little map of California. Obviously, we wouldn't use these in a model. Please don't. But then you get things like DEM. Here's our elevation and our minimum temperature. Sure enough, as you go up in elevation, your temperatures go down. So they're strongly correlated, 0.88. So we would only use one of those in our model. I, of course, prefer temperature. Now, min and max temp, interestingly enough, don't correlate as much, right? So that's interesting. You might use both min and max because of that. Okay, very important charts. Correlation plots, this is just a simple version between a few of them. This is what I'd love to see in your reports rather than the more complex ones. These are there for you to do analysis and pick your covariates. These are there for you to report on. Okay, so again, looking at your models, this is where we're starting to move from looking at the data just in and of itself to looking at, can we model this data using our covariates? In other words, can we build good models using the data that you have? So the main tools for doing that for occurrences is going to be a histogram, and you're histogramming your covariates at the occurrence points versus the entire area, or all the covariate. For binary data, you histogram each value. Now for both of these, what you're looking for is with those two histograms you're going to get, is there a difference? In other words, where there's zeros in your histogram from binary data that has zeros, is it a different histogram from your binary data that has ones? If those two histograms are identical or close to identical, you're not going to be able to model it using those covariates. So there's no point moving forward. Now the same is true for occurrences, except note that your histogram covariates for your occurrences is always going to be a subset of the overall covariates, right? So you're looking for them to be different, but don't expect them to be two separate distributions, two separate histograms. They're going to overlap, but the question is it a fairly small subset where your occurrences are? For categorical data, it's the same idea where you're doing histograms of covariates for each value. In other words, if you've got 5 values, you're going to go ahead and make a histogram for each value in your categorical data. However, if you end up with 100 categorical values, which is a little bit shaky anyway, and you don't really want to run a histogram for each one and try and look at them, just run a scatter plot. Now, hopefully you have ordinal data, some data that has some type of order to it, so that you can order the scatter plots and see if there is a relationship there. For continuous data, it's scatter plots, and again, you'll see a relationship. If you don't, really probably don't go forward with modeling with those covariates. It's time to look for other covariates. So as an example, here's our precipitation of Doug fir, and this is where Doug fir occurs from the FIA data. If we histogram that, here's the Doug fir where they occur in California. If we histogram that against all of California, which is this green line, we see, wow, there's quite a difference. Now, this has been scaled so that both of these histograms go to 1, okay, so we can look at them, because otherwise this one will be way down here and it'd be hard to see what's going on. So it's just been scaled to be bigger, okay, and this is from HEMI, by the way. So this shows, yeah, California has a lot of dry land, dry desert land, and there's very little Doug fir there. But you get up here where it's wet, now we're seeing Doug fir. And because of this distinction, because there's a difference between these two histograms, that's an indication that we can build a successful model for Doug fir. When we look at Doug fir height versus precipitation, a little bit harder to see the model. There is a model there, but it's a little bit harder to see. And we also see there's some zeros, some annual precipitation of 0, and there's some zero heights. So there may be some problems here. This is why we want to graph stuff, because this is showing we may have a few issues here in our data that we want to take a look at. So if we take this data and instead we do maximum height versus precipitation, suddenly the picture's very different, right? Suddenly we can see, yeah, Doug Fir maximum height, has got this nice relationship that we can probably model with a GAM. Not sure what's going on over here. We probably need to go check that because there's something strange that happened around 0, which will happen, and we'll talk more about that. All right, so to look for predictors, these are common ones on the ground. Slope, aspect, absolute aspect, distance to. There's a whole bunch of distance to ones that we've used in the past successfully. Distance to roads and streams, especially for things that impact humans or things like beavers that, of course, are going to be near streams or streamlines, which we can get. Climate, temperature, precipitation, a few other climate types. Soil is really hard. We don't have very good soil data. It's very blocky. It's missing, got a lot of gaps. Sometimes we can do surface cover, more successful in soil type, unless you have a small area. If you've got a small area, especially if they dug soil pits, you can do some cool stuff with soil. Remote sensing, we have all kinds of stuff. Not only the raw remote sensing data from the satellites, but a whole bunch of derived layers that often we can work with to get good models. In the marine world, we have less good data. And sorry about that. But we do have temp, dissolved oxygen, salinity, depth, rugosity, current at depths, and wind. So we do have some layers. It's just harder. And it's sea surface temperature is the temp that we usually have. Dissolves oxygen we usually have near the field sites or the buoys. So it is a challenge, but we've done it in the past. Talk to me if you have marine stuff. Now, depending upon your species, things can get more complicated. So if your species requires another species, and this is really true when we start getting into predator-prey relationships, it happens a little bit with allopathy and symbiotic relationships with plants, but the higher trophic level your species is at, such as high-level predators, eagles, bears, mountain lions, it becomes more difficult to successfully model them because of those complexities and because they have brains and they make decisions as to where they're going to hunt based on things other than environmental variables that we can get covariates for. And then there's also temporal and cyclical stuff that make things more complicated. Now, there's all kinds of different predictor layers. Don't think you've just got precipitation. You have min precip, maximum precip, because plants tend to respond to minimum precipitation when they dry out and die, or maximum precipitation when they get too wet, get fungal infections, and die that way. So they like that in-between range, but it's the min and the max that sets whether they can be successful, usually more than the means. I find the min and the max to be more successful than the means. Sometimes it's the range of values. Colorado can have 70-degree Fahrenheit temperature shifts in a 24-hour period. Not all plants and animals can deal with that. Not all humans can deal with that. Heterogeneity, how complex is the environment? So that's another one to look at. That's the rugosity one that's used in the marine world quite a bit because some species like it where there's a lot of roughness, a lot of things going on, which means there's a lot of other species and things happening. And then don't forget that you can do derived layers such as distance to things, and of course we have all kinds of topography layers that are derived from elevation, slope, aspect, rugosity, things like that. Okay, so when you're looking at field data, one key is to get as close to the field measurements as possible. If you can get the field data and get your field crews to put the data into an electronic device like a spreadsheet or a tablet, and then you get that data, that's going to make you more successful. As few steps for them to copy it and make mistakes as possible, or you to copy and make mistakes. Clean and aggregate the data as needed as you go. As you're out collecting the data, you want to be cleaning it. You want to be looking at it right away as soon as you can in case there's mistakes, so you can fix those and often fix your protocol in the field to improve the quality of the data. Estimate the overall uncertainty. We'll talk quite a bit about that. And then really keep looking at what's the spatial temporal measurement scales that are appropriate to model given the data. In other words, if you're just working in a small area, if you're working in Rocky Mountain National Park, Redwood National Park, okay, you're going to have to be careful trying to use that model for all of California. Okay, if that's all the data you've got is for Redwood National Park, Redwood National Park, it's not going to work to model it in California, but we can get data for the rest of California. Okay, it may not be the same quality or the same depth of what you're looking for, the same measurements, but we can get data. So that may change not only your modeling approach, but the questions that you're going to ask. All right, finally, watch out for temporal issues. If you're modeling something like change over time, or you're modeling phenology, you will need to get data broken up probably into months, sometimes seasons, sometimes years for like climate change, or even decades. Okay, but the key there is being consistent between predictors and response. In other words, making sure your predictors and your response variables are also from those same temporal slices that you're working with. And again, get your predictors as close to the sample locations and dates as possible. And then in everything that we're doing, use the best predictor layers you can and the best covariates for your models, the best independent and dependent data you can get. That'll answer your questions.